Let me go through a simple hypothesis set in detail so that we have something to implement. So after the lecture, you can actually implement a learning algorithm on real data if you want to. This is not a glorious model. It's a very simple model. On the other hand, it's a very clear model to pinpoint what we are talking about. Okay, so here is the deal. Okay, you have an input, and the input x1 up to xd, as we said, the d-dimensional vector, and each of them comes from the real number, just for simplicity. So this belongs to the real number. And these are the attributes of a customer, as we said, salary, years in residence, and whatnot. So what does the perceptron model do? It does a very simple formula. It takes the attributes you have and gives them different weights W. Okay? So let's say the salary is important. The chances are W corresponding to the salary will be big. Okay? Some other attribute is not that important. The chances are the W that goes with it is not that big. Actually, outstanding debt is bad news. If you owe a lot, that's not good. So the chances are the weight will be negative for outstanding debt, and so on. Now you add them together, and you add them in a linear form. That's what makes it a perceptron. And you can look at this as a credit score of sorts. Okay? Now you compare the credit score with a threshold. If you exceed the threshold, they approve the credit card. And if you don't, they deny the credit card. So that's what they settle on. They have no idea yet what the W's and the thresholds are, but they dictated the formula, the analytic form that they are going to use. Okay, so now we take this and we put it in the formalization we had. We have to define a hypothesis, small h, and this will tell us what is the hypothesis set that has all the hypotheses that have the same functional form. So you can write it down as this. This is a little bit long, but there is absolutely nothing to it. This is your credit score, and this is the threshold you compare to by subtracting. If this quantity is positive, you belong to the first thing, and you will approve credit. If it's negative, you belong here, and you will deny credit. Well, the function that takes a real number and produces the sign +1 or -1 is called the sign. So when you take the sign of this thing, this will indeed be +1 or -1, and this will give you the decision you want. And that will be the form of your hypothesis. Now, let's put it in color. And you realize that what defines H is your choice of Wi and the threshold. These are the parameters that define one hypothesis versus the other. X is an input that will be put into any hypothesis. As far as we are concerned, when we are learning, for example, the inputs and outputs are already determined. These are the data set. But what we vary to get one hypothesis or another, and what the algorithm needs to vary in order to choose the final hypothesis are those parameters, which in this case are Wi and the threshold. Okay. So let's look at it visually. Let's assume that the data you are working with is linearly separable. Linearly separable, in this case, for example, you have 9 data points. And if you look at the 9 data points, some of them were good customers and some of them were bad customers. And you would like now to apply the perceptron model in order to separate them correctly. You would like to get to this situation where the perceptron, which is this purple line, separates the blue region from the red region or from the pink region. And indeed, all the good customers belong to one, and the bad customers belong to the other. So you have hope that a future customer, if they lie here or lie here, they will be classified correctly, if there is actually a simple linear pattern to this to be detected. But when you start with random weights, and the random weights will give you any line. Okay? So the purple line in both cases corresponds to the purple parameters there. Okay? One choice of these W's and the thresholds correspond to one line. You change them, you get another line. So you can see that the learning algorithm is playing around with these parameters and therefore moving a line around, trying to arrive at this happy solution. Okay. Now we are going to have a simple change of notation. Instead of calling it threshold, we are going to treat it as if it's a weight. It was minus threshold, now we call it plus W0. Absolutely nothing. All you need to do is choose W0 to be minus the threshold. No big deal. Okay. So why do we do that? We do that because we are going to introduce an artificial coordinate. Remember that the input was x1 through xd. Now we are going to add x0. This is not an attribute. an artificial constant we add, which happens to be always +1. Okay, why are we doing this? You probably guessed. Because when you do that, then all of a sudden the formula simplifies. Now we are summing from I equals 0 instead of I equals 1. So you added the 0 term. And what is the 0 term? It's the threshold which you conveniently call W0 with a plus sign, multiplied by the 1. So indeed, this will be the formula equivalent to that. So it looks better. Okay? And this is the standard notation we are going to use. Okay? And now that we put it in as a vector form, which will simplify matters. So in this case, you will be having an inner product between a vector W, a column vector, and a vector X. Okay? So the vector W would be W0, W1, W2, W3, W4, etc. And X0, X1, X2, etc. And you do the inner product by taking a transpose, and you get a formula which is exactly the formula you have here. So now we are down to this formula for the perceptron hypothesis. Okay. Now that we have the hypothesis set, let's look for the learning algorithm that goes with it. The hypothesis set tells you the resources you can work with. Now we need the algorithm that is going to look at the data, the training data that you are going to use, and navigates through the space of hypotheses to bring the one that is going to output as the final hypothesis that you give to your customer. So this one is called the perceptron learning algorithm. And it implements this function. And what it does is the following. It takes the training data. That is always what a learning algorithm does. This is their starting point. So it takes existing customers and their existing credit behavior in hindsight. That's what it uses. And what does it do? It tries to make the W correct. So it really doesn't like at all when a point is misclassified. Okay, so if a point is misclassified, it means that your W didn't do the right job here. So what does it mean to be a misclassified point here? It means that when you apply your formula with the current W, the W is the one that the algorithm will play with, apply it to this particular X, then what happens? You get something that is not the credit behavior you want. It is misclassified. Okay? So what do we do when a point is misclassified? We have to do something. So what the algorithm does, it updates the weight vector. It changes the weight, which changes the hypothesis, so that it behaves better on that particular point. And this is the formula that it does. So I'll explain it in a moment. Let me first try to explain the inner product in terms of agreement or disagreement. If you have the vector X and the vector W this way, their inner product will be positive, and the sign will give you a +1. If they are this way, the inner product will be negative, and the sign will be -1. So being misclassified means that either they are this way, and the output should be -1, or it's this way, and the output should be +1. That's what makes it misclassified, right? Okay, so if you look here, at this formula, it takes the old W and adds something that depends on the misclassified point, both in terms of the xn and yn. Well, yn is just plus or minus 1. So here you are either adding a vector or subtracting a vector. And we will see from this diagram that you are always doing so in such a way that you make the point more likely to be correctly classified. How is that? If y equals +1, as you see here, then it must be that since the point is misclassified, that w.x was negative. Now, when you modify this to w plus yx, it's actually w plus x. So you add x to w, and when you add x to w, you get the blue vector instead of the red vector, and lo and behold, now the inner product is indeed positive. And in the other case, where it's -1, it is misclassified because they were this way. They gave you +1 when it should be -1. And when you apply the rule, since y is -1, you are actually subtracting x. So you subtract x and get this guy, and you will get the correct classification. Okay, so this is the intuition behind it. However, it's not the intuition that makes this work. There are a number of problems with this approach. I just sort of motivated that this is not a crazy rule, whether or not it's a working rule that is yet to be seen. Okay, so let's look at the iterations of the perceptual learning algorithm. Okay, so here is one iteration of PLA. So you look at this thing. And okay, you have this current W corresponds to the purple line. This guy is blue in the red region. It means it's misclassified. So now you would like to adjust the weights, that is, move around that purple line, such that the point is classified correctly. If you apply the learning rule, you will find that you are actually moving in this direction, which means that the blue point will likely be correctly classified after that iteration. Okay? There is a problem, because let's say that I actually move this guy this direction. Well, this one, I got it right, but this one, which used to be right, now is messed up. It moved to the blue region, right? And if you think about it, I'm trying to take care of it, and I may be messing up all other points because I'm not taking them into consideration. Well, the good perceptual learning algorithm is that all you need to do is for iterations 1, 2, 3, 4, etc., pick a misclassified point, any one you like, and then apply the iteration to it. The iteration we just talked about, which is this one, okay, the top one. And that's it. If you do that, and the data was originally linearly separable, then you will end up with the case that you will get to a correct solution. You will get to something that classifies all of them correctly. This is not an obvious statement. It requires a proof. The proof is not that hard, okay? But it gives us the simplest possible learning model we can think of. It's a linear model, and this is your algorithm. All you need to do is be very patient, because 1, 2, 3, 4, this is really long. At times it can be very long. But it continues. That's the promise, as long as the data is linearly separable. Okay? So now we have one learning model, and if I give you now data from a bank, previous customers and their credit behavior, you can actually learning algorithm and come up with a final G that you can hand to the bank. Not clear at all that it will be good, because all you did was match the historical record. Well, you may ask the question, if I match the historical records, does this mean that I'm getting future customers right, which is the only thing that matters? The bank already knows what happened with the previous customers. It's just using the data to help you find a good formula. The formula will be not good to the extent that it applies to a new customer and predicts the behavior correctly. That's a loaded question, which will be extreme detail when we talk about the theory of learning. That's why we have to develop all of this theory. Okay, so that's it, and that is the perceptual learning algorithm.